Welcome to The Explainer, made by Forge College. I'm your host, and today I'm stepping into the role of your systems architect. We've covered a ton of ground in this module, exploring blockchain in action, but right now, it's time to literally draw up the practical blueprints for taking blockchain from a fascinating theory and dragging it into cold, hard reality. Today's Explainer is all about adoption challenges and next steps. Let's get to work. So, let's start with a very practical, maybe even slightly painful question that you might already be asking yourself. Why is adding a blockchain to your tech stack so incredibly complicated? I mean, if you just listen to the marketing pitches, blockchain sounds like absolute magic, right? You just plug it in and boom, instant trust, perfect data, zero problems. But as you and I both know, actually plugging a distributed ledger into a living, breathing tech stack, yeah, that's a gritty, boots-on-the-ground engineering challenge.
Okay, let's dive into this. Here's our architectural blueprint for your upcoming capstone. We'll start by going from theory to reality, then tackle the operational complexity challenge. Look at tackling legacy system integration, weigh performance and scalability trade-offs, discuss governance, risk, and resilience, and finally, build out your capstone integration plan.
Step 1. From theory to reality. Bridging the gap.
Now, in our previous lesson covering logistics, identity, and healthcare insights, we saw firsthand just how incredible auditability and provenance can be. I mean, it really is revolutionary. But translating those massive theoretical benefits into reality, that requires a very careful balancing act. You've got to balance strict engineering constraints against messy organizational trade-offs. We're moving completely away from those broad marketing claims, right down into the nuts and bolts of mechanistic engineering here. That means worrying about the gritty details, like interoperability with legacy databases and the very real need for selective privacy. Which brings us right to our first major hurdle. Section 2, the operational complexity challenge, managing the chaos. Understanding what operational complexity actually means in this context is absolutely crucial. It's basically the friction that emerges because adding a replicated state machine creates multiple new coordination surfaces. Think about it practically. You're now forcing schema migrations on two totally different systems simultaneously, or you're trying to maintain compatibility during rolling upgrades. Imagine you're in the billing department for a big logistics firm. You have a shipment record sitting on a brand new ledger, and you have one on your ancient ERP system. So, which one is the canonical source of truth? Making just that single decision totally changes your entire testing and error handling logic across multiple teams. That friction right there, that is operational complexity. Next up, Section 3, tackling legacy system integration, culture clash.
We are facing a severe architectural mismatch here. On one side, you have your legacy ERP system. It absolutely loves batch-oriented data models, it's totally centralized, it's got these brittle APIs and very tightly coupled workflows. And then, on the other side, you have your shiny new distributed ledger. It lives in real-time decentralized state, relies on multi-party consensus, push-based synchronization, and immutable assertions. Honestly, trying to integrate these two things is literally like trying to plug a modern USB-C drive into a 1990s floppy disk reader. It's rough.
So how do we actually fix it? Well, there are three main integration patterns, but I want to be perfectly clear. Each one comes with a specific cost that you have to pay. First, we have integration adapters. These translate formats nicely between the two systems, sure, but they add frustrating runtime bottlenecks. Second is push-based synchronization. This writes ledger assertions directly to your legacy stores, but because of the huge increase in writes, it almost always causes contention. And third, architecture migration. This is where you just bite the bullet and actually move your workflows over to ledger-native services. It's definitely the cleanest approach, but man, it costs significant time and refactoring effort.
Moving on to Section 4, performance and scalability trade-offs, the latency game.
You know, scalability isn't just about raw throughput numbers. It's heavily about the cost of scaling and just how sensitive your specific application is to latency. When you're dealing with scalability, your specific application constraints directly dictate your architectural choices. It's like a giant puzzle. If your main criterion is latency, like, hey, what's the maximum response time allowed? Well, you might need off-chain caching to hit those snappy sub-100 millisecond speeds. If privacy is your key constraint, you're looking at permission channels or on-chain hashes. Need crazy high throughput for peak TPS? You'll have to consider batching or sharding. Got complex governance requirements with multiple approval bodies? You're likely looking at permission ledgers. Simply put, your constraints build your architecture. Let me give you a concrete number to really anchor this. 150 milliseconds. If we simulate synchronous on-chain writes using just a simple Python script, waiting for a network to actually reach consensus might average around 150 milliseconds. Now, if you're building a modern front-end application that needs snappy, sub-100 millisecond responses to keep your users from getting annoyed, a 150 millisecond synchronous write is going to completely fail your acceptance criteria. No way around it.
So we have to look for workarounds. One popular option is batched writes. Accumulating your writes into a batch significantly lowers the initial per-request latency. That's your baseline, it looks great. But this triggers a massive spike in what we call tail latency when that batch finally commits or flushes to the ledger. The requests that are just sitting at that flush boundary, they take a huge hit in wait time.
Another alternative is the cache-then-anchor pattern. Caching off-chain gives your users lightning-fast, immediate local read and write responses. But again, there's a trade-off. Actually, scratch that, it's more like a calculated compromise. You incur a high delay in ledger immutability. You are consciously trading immediate ironclad security for user speed, choosing to anchor the data to the ledger periodically instead of instantly.
Step 5. Governance, risk, and resilience, the human factor. Because so often the absolute hardest part of building distributed systems isn't the code, it's distributing the human decision-making. Governance costs are basically organizational frictions, things like voting, arbitration, and complex change control processes. These consume massive amounts of time and create enormous points of failure when multiple different stakeholders have to agree on protocols. Honestly, getting governance agreement across different enterprise organizations is like trying to get 5 completely different departments to agree on a single pizza topping. It's messy, it takes forever, and everyone wants something different.
And this deeply affects our risk and resilience. We have to completely shift our mindset from just worrying about a simple single database outage to planning for Byzantine behaviors and bad actors. You must actively plan for network partitions and quorum thresholds. It requires advanced tooling like service meshes and replay and reconciliation tools. And multi-party disaster recovery exercises? Yeah, those aren't optional anymore. They are strictly mandatory. By the way, if you want to explore these specific failure domains in much greater depth, Forge College has some fantastic additional courses and programs on Web3 systems that I highly recommend you check out. Because resilience, it has to be actively engineered. You can't just hope for it.
Finally, Section 6, your capstone integration plan. Time to build. Okay, here is your ultimate blueprint checklist. These are 5 repeatable steps that you'll use to prioritize your engineering actions for your capstone project. Step 1. Gather constraints. Find out exactly what your application actually needs. Step 2. Map patterns directly to those constraints. Step 3. Define mitigations for where those patterns inevitably fall short. Step 4. Specify governance, literally who decides what. And Step 5. Set acceptance criteria and rollback plans.
I really want to zoom in on Step 5 for a second. Acceptance criteria or service level objectives. These are measurable success parameters, monitoring dashboards, and incredibly concrete rollback plans designed specifically to reduce risk during that critical first production release. I literally cannot stress this enough. These criteria convert your vague, abstract worries into actionable, observable targets. This is exactly what will make your capstone plan credible and actionable to a rigorous enterprise stakeholder or a skeptical operations team.
So, if you take absolutely nothing else away from this explainer, please remember this core philosophy. Treat adoption barriers as standard engineering tasks, not magical deal breakers. If you map your constraints, if you prioritize governance from day one, and if you simulate your loads to truly understand your latency, you can safely and effectively integrate blockchain into reality. It just takes structured discipline. Which leaves me with a final, provocative thought for you to carry forward. How will you balance the pure, theoretical ideal of decentralization with the gritty, real-world constraints in your own capstone blueprint? Think deeply on that as you start sketching out your plans. I want to thank you so much for joining me for this explainer made by Forge College. To learn more about this subject and explore a whole community of other Web3-related topics, please visit forge.college. Keep learning, keep building, and I will see you in the next one.